In this next video, we're going to look at an example with multiple linear regression by just kind of talking through both how to interpret the coefficients as well as the t-tests and what they now represent when we're doing multiple linear regression. So here's an example where we're going to model a boy's height, or I guess maybe it's, I don't know what age it is, honestly. Maybe it is when that boy is an adult. Maybe it is when that boy is still some certain boy age. But we're going to use these two predictors, and that is mother's height and father's height as predictor of boy's height. And so we have, I guess, about 100-ish, 134, I think, boys and their parents' heights in this particular sample. And so we fit a model and we got the following regression output. And so the first thing we're going to do is look at the hypothesis tests that are being completed for each of these predictors. So you'll still notice that we have a t-test for each of our predictors, one for mother's height as a predictor, one for father's height as a predictor. And so in each case, we have a beta coefficient estimate. So what we estimate that that coefficient is in the model. We have the standard error, meaning this is how much error we expect in our estimate, how far we would expect to be off on average when we fit this with this particular size data with this much variability in the data. We can now create a t-test to determine how many standard errors away we are from zero. So zero would be no slope. It would be no relationship or no contribution in this particular model. And so we can see that we are about 3.014 standard errors away from zero with our estimate. And we can then run a t-test and see that the p-value of this t-test is 0.21%. That is less than 1%, meaning that if there really was no relationship, if it really was a zero slope for mother's height in this model, if mother's height was not contributing to this model, then we would see this much correlation by random chance only about 0.21% of the time. So that's giving us some very strong evidence that the coefficient really is not zero, that the coefficient is some value, in this case, greater than zero. So we have some pretty strong confidence that there is at least some relationship or some contribution from mother's height in this model. But something that we need to notice here as well is that it's not just mother as a solo predictor. It's not just mother's height as the only predictor here, but it's mother's height if we already have father's height in the model. In other words, it is how confident we are that mother's height is a predictor of boy's height for fathers of the same height. In other words, if father's height stays constant and we're looking at different mother's heights in that context, do we see a relationship with boy's height and mother's height when father's height is staying the same? And so that is going to be the difference that we need to recognize when we write out these null hypotheses. So we're actually going to have two nulls, one for each predictor in this case. So the null here would be that there is no, and then kind of in parentheses linear, because we're kind of assuming we're fitting a linear term, so we're saying linear, even though technically if it was not a linear relationship, it would look kind of like this. That would show up as something in this test, because our test does not differentiate what type the relationship is, only that the relationship is non-zero. So the null is going to be that there is no relationship, and in parentheses linear, no linear relationship. Between mother's height and son's height when father's height holds constant. All right, and then we can do the same thing here for father's height. So the null hypothesis here for that is that there is no, again, linear, but really just any kind of non-zero relationship. Between father's height and son's height when mother's height holds constant. All right. Okay, and so we're going to judge each of these, and we're also going to interpret our adjusted R squared as well. So we talked about this a little bit earlier in the previous video. So our adjusted R squared is 49.71%. So we're going to say that 49.71% of the variability in a boy's height, or I guess instead of saying a boy, singular, I'm going to say like in boy's height because it is a variable with many observations in it. So in boy's height, the variable is explained. And I could just say by this model if I don't want to be wordy and list all the predictors, but there's only two, so that's not really going to take that long, is explained by the linear relationship with mother and father's height and since this is adjusted R squared, I am going to kind of add a tag here at the end, and I'm going to say after adjusting for correlation due to random chance. So in other words, this value is actually slightly lowered from the true R squared value that would be measured here. And it's lowered, it's adjusted based on how much correlation I would expect to explain by random chance by adding two predictors into this model. And so we do that again because I can keep adding predictors into a particular sample of data, and I can keep fitting the R squared higher and higher and higher and getting closer and closer to 100%. But if I only have a sample of data and I keep fitting it on the same sample, then I'm going to start overfitting. Because if I'm including on the same sample of data, well, I can always adjust the coefficients to explain a little bit more on the same sample of data. But then I get to a new set of data and my model is completely, overfit. It's not actually making any real predictive power when it gets to a new set of data. So that's why adjusted R squared can kind of be helpful as a quick reference here to see how much variability I'm probably really explaining by taking out the kind of the random chance variation that I probably get when I just add another predictor into this particular sample of data and possibly begin overfitting there. So let's go ahead and interpret the coefficients in context now. So for every 1 unit increase in, we'll start with mother's height, it's listed first. We expect son's height to increase by 0.0503 55 as father's height is holding constant. So if we're looking at fathers of the same height, and we look at mothers who are 1 unit difference, I'm guessing it'd be like 1 inch difference. And this is the difference in son's height that we expect to see on average. We expect to see sons increase by 0.05 inches when mother's height increases by 1 and father's height is staying the same. We can also do this with every 1 unit increase in father's height. And we're going to say we expect son's height to increase by 0.217 as mother's height holds constant. So if we're looking at mothers of the same height, but fathers of 1 maybe inch difference, then we're expecting son's height to be increasing or changing by this particular amount. I am not clicking on my face there. There we go. Okay. So 0.217143 is the average expected change in son's height when we do that. So again, I really should have wrote the word average in here. I think I just copied and pasted from the previous page, and in both cases I didn't really notice that that word was missing. So yeah. All right, and then let's also kind of go over here. What should we conclude about these predictors? Are they good linear predictors of sun's height? Do they both contribute to this model? And so this is where those p-values probably come in to this conversation. Is we can see that the t-tests of both of these variables show the p-values quite low, meaning that we're quite confident that each of these is contributing to the model. Even when I already have information from the other one, I'm still quite confident that the other is adding additional explanatory power here to sun's height. So, so because the p-values are each low, we have confidence that both predictors are contributing to the model. And that kind of makes sense contextually here, because now I'm sure that there is some correlation between mother and father's height. If you think about, you know, a man and a woman who, you know, not to have the talk with y'all here, but who get together, you know, maybe there is some correlation in height between between matches like that, that maybe you don't, you know, always see kind of random pairings, but rather tall people and tall people might go together. Maybe short people and short people are more likely to go together. But there's certainly going to be at least some independence. So there's going to be some kind of randomness in heights. So it makes sense that both biologically, both the height of both parents is going to matter, and also that the predictors themselves, mother's height and father's height, are not going to be highly correlated, maybe a little bit correlated, but not highly correlated. Thus, they will be explaining, you know, unique variability in the response variable, most likely. All right, and then we should also add here, you know, are they good linear predictors? Well, this is only telling me if I'm confident that they are predictors at all, but I should probably add that the r squared value, so r squared, and at this point we could just say adjusted r squared is 49%, meaning that we're probably explaining somewhere around 49-ish% of the variability in sun's height, which is probably pretty good. Nobody can really tell you what a great r squared is. It's kind of hard to put a criteria on it or a threshold on it. But if you think about it, the fact that we're explaining 49% of the variability in sun's height with two predictors, I mean, that's some good headway. So explaining a sizable percent of variability. So I would say they're probably pretty good predictors there. If you think about, you know, what other predictors are available that we could think of. Let's say that the adjusted r squared value for a model, including just father's height as a predictor, is 0.4365, and the adjusted r squared for mother's height is 0.2856. Is it a good idea to include both, or should we stick with just one of the simple regression models? So the difference here, if we compare it to the highest solo predictor, is going to be 0.4971 minus 0.4365, and that's going to be about 0.0606, about 6%. So that's pretty good. And if you also think about the fact that there's, in the case of the best solo predictor model, there's about 57% unexplained variability if we only include father's height, and we improve that to about 51% when we have both father and mother's height. So we are explaining a good chunk of the remaining variability. So So 57% unexplained with father only. And we kind of improve that here to 51% unexplained with father and mother. So, I mean, if I'm thinking about that 1/20th rule that we mentioned earlier, which again is a very loose way of thinking about this, I'm certainly beating that by quite a bit. That I am explaining about 6% out of 57% of the unexplained variability, which is much better than 1/20th. I think that's going to be about somewhere a little bit better than 1/10. I think my phone's it has enough left here. What is that going to be? 6 divided by 57. I get about, yeah, 0.105. So, so certainly better than 1/20th. And again, even if it was less than 1/20th, it doesn't necessarily mean that I shouldn't add the other predictor, but just that I should question it, that I should think, it's not a lot. So is this an easy variable to access? Is this a sensible variable? Am I concerned about having like a whole lot of variables that maybe I don't want all these variables? So I would say, yeah, in this case, this is explaining a fair amount of additional variability. I think it makes sense to add mother's height as a predictor in this model. So yeah, we'll stop there.